Thanks to CuriosityStream for sponsoring this video. Engineering materials are normally split into 4 categories: metals, polymers, ceramics, and composites. Understanding the different types of materials, their properties, and how to use them effectively is a crucial part of engineering. In this video, we'll explore metals, their microstructure, and different techniques like alloying and heat treatment that can be used to improve their properties. Around 2/3 of the elements in the periodic table are metals, although for engineering purposes, we're particularly interested in just a handful of them. Iron is probably the most important of them all, because it's used to create steel, a high-strength material with a wide range of engineering applications. Aluminum is commonly used because its alloys have high strength-to-weight ratios. It has a relatively low melting temperature, which makes it easier to process and use for casting, and it's relatively inexpensive. Like aluminum, titanium has excellent strength-to-weight properties, although it is even stronger, making it a popular choice for aerospace applications. Its high melting point makes it suitable for applications at high temperatures, but makes processing more difficult. It's also much more expensive than aluminum. Other important metals include magnesium, copper, and nickel. The key to using these metals effectively lies in understanding how they're structured at the atomic level. The atoms of a pure metal are packed together closely and are arranged in a very regular grid. Because of this regular structure, metal is what we call a crystalline material, and the grid the atoms are arranged in is called the crystal lattice. Not all materials have a regular structure like this. In glass, for example, the atoms are arranged randomly, so it's an amorphous material, not a crystalline one. We can think of the crystal lattice as a repeating number of identical units that we call the unit cell. There are several different ways the atoms of a metal can pack together, which means that there are several different types of unit cell. At room temperature, copper atoms, for example, pack together as shown here, where there is an atom at the corner of each unit cell and one at the center of each face. We can see this better if we shrink the size of the atoms and display the bonds between them. This is called the face-centered cubic structure, or FCC. But iron atoms prefer to pack together in a structure where the atoms at the center of each face are replaced by a single atom in the middle of the unit cell. This is the body-centered cubic structure, or BCC. And titanium atoms prefer to pack together in what's called the hexagonal close-packed structure. These are the 3 most common crystal structures in metals. Both the FCC and the HCP structures have a packing factor of 74%, meaning that the atoms occupy 74% of the total volume of the unit cell. The BCC structure is slightly less closely packed, with a packing factor of 68%. The close packing of the atoms is one of the reasons metals have much higher densities than most other materials. In reality, lattices aren't perfect like the one shown here, but contain numerous defects, of which there are several different types. A vacancy defect occurs when an atom is missing from the lattice. An interstitial defect occurs when an atom squeezes into the gap between existing atoms in the lattice. This is a self-interstitial defect, since the extra atom is of the same element as the lattice, but interstitial defects can also be created by impurity atoms of a different element. And then we have substitutional defects, where certain atoms in the lattice are completely replaced by impurity atoms. These are all point defects, because they affect a single location within the lattice. Lattices also contain linear defects, called dislocations, where a number of atoms are offset from their usual position in the lattice. The first type of dislocation is an edge dislocation, where the lattice contains an extra half plane of atoms. Let's shrink the atom size so that we can show the atomic bonds. This is a stable configuration, but when a stress is applied to the lattice, the atomic bonds break and reform, allowing the extra half plane of atoms to glide through the lattice. Another type of dislocation is the screw dislocation, where an entire block of atoms is shifted out of alignment with the perfect lattice structure. It gets its name because if you follow a path of atoms around the dislocation, it will spiral down through the lattice like the thread of a screw. Again, when a shear stress is applied, the atoms rearrange into a new stable configuration. Most real dislocations will actually be a combination of edge and screw dislocations. Because dislocations move through the lattice by the breaking and reforming of atomic bonds, the process is irreversible. A dislocation doesn't return to its original position when the applied shear stress is removed. This is the underlying mechanism behind plastic deformation in metals. It's essentially the motion of a large number of dislocations at the atomic level. Elastic deformation is caused by the stretching of atomic bonds. Unlike the motion of dislocations, this stretching is completely reversed when the load is removed. This graph shows how a material's yield strength changes with dislocation density. Materials that contain a large number of dislocations have improved strength, because dislocations can get tangled, preventing each other from moving through the lattice. The motion of dislocations through the lattice is also affected by how the atoms pack together. It's easiest for dislocations to move along planes where the atoms are closest to each other, since it's easier for those bonds to break and reform. This corresponds to different planes depending on the structure of the unit cell. In reality, even pure metals don't maintain a regular crystalline structure over long distances. Let's zoom in to some molten metal and see how it solidifies. As the metal cools down, atoms group together and a lattice structure begins to form in several different locations at the same time. Each of these lattices has its own orientation, and as the metal cools down, the lattices continue to grow until it has completely solidified. We end up not with one continuous lattice, but with multiple lattices that are oriented in different directions. This creates what we call grains within the metal structure, and materials made up of a collection of these grains are said to be polycrystalline. The grains are separated by grain boundaries. Since each grain has specific planes along which it's easier for slip to occur, the presence of grains impedes the motion of dislocations, and so polycrystalline materials tend to be stronger than materials made up of a single uniform crystal. The smaller the grain size, the stronger the material will be. This is captured in the Hall-Petch equation. We can use this information to intentionally strengthen metals by controlling the size of the grains that form as the metal is cooled. Impurities called inoculants can intentionally be added to the molten metal so that crystal nucleation occurs at more sites than it otherwise would have, leading to smaller grain sizes. Another way we can do this is by controlling how fast the metal is cooled. If a metal is cooled very rapidly, nucleation occurs at more locations and the crystals don't have much time to grow, so the metal will end up with a finer grain structure and will be stronger as a result. Controlling grain size to strengthen a metal is called grain boundary strengthening. This is just one of many strengthening techniques. We can also strengthen a metal by plastically deforming it, using techniques like cold rolling or forging. This increases the number of dislocations, and so increases the strength of the material at the cost of reducing its ductility. This is called work hardening. One very useful quality of metals is that they can be mixed with small quantities of other metallic and non-metallic elements to improve the properties of the base metal in some way. Metals that are created by combining different elements in this way are what we call alloys. We typically split metals and their alloys into ferrous and non-ferrous categories, depending on whether or not the base metal of the alloy is iron. Brass, for example, is a non-ferrous alloy of copper and zinc. It typically contains 65% copper and 35% zinc, although other alloying elements are sometimes added. It is used for its attractive appearance and the ease with which it can be machined. Aluminum alloys are important in engineering and are often used for the good strength properties they provide at a light weight and reasonable cost. Common alloying elements are copper, manganese, silicon, zinc, and magnesium. Aluminum alloys are classified according to whether they're designed to be used for casting or to be worked, and are designated using specific numbering systems. But steel is probably the most important engineering alloy of all. Pure iron is too soft for it to be used for structural purposes, but it can be combined with small amounts of carbon, and in some cases, other elements, to produce steels that have incredibly useful properties. Steels are separated into a few different categories, depending on the amount of carbon and other alloying elements. Low carbon, or mild steel, contains up to 0.25% carbon. It doesn't have particularly high strength, but is ductile and relatively low cost. Medium carbon steel contains between 0.25 and 0.6% carbon, and high carbon steel contains between 0.6% and 2% carbon. Since these steels contain a larger amount of carbon, they are stronger and can be more easily strengthened using different heat treatment methods, like quenching and tempering. Between 2% and 4% carbon, we obtain cast iron. It has good fluidity, and the additional carbon lowers the melting point of the alloy, making it good for casting, although it tends to be brittle. We can add additional elements to the iron-carbon mix to obtain specific properties. Stainless steel, for example, incorporates chromium to provide resistance to corrosion, the most common being Type 304 stainless steel that contains 18% chromium and 8% nickel. Alloys are created by melting the base metal and various alloying elements together. They can either be substitutional or interstitial, depending on the relative size of the atoms. Steel is an interstitial alloy because the atomic radius of carbon is much smaller than the atomic radius of iron. The presence of alloying elements distorts the crystal lattice, which tends to impede the motion of dislocations, and so has a strengthening effect. This is called solid solution strengthening. But the alloying elements aren't always able to fully dissolve into the base metal's lattice. If an alloying element is added beyond a certain saturation point, it can separate out and produce a distinct homogeneous phase within the metal's microstructure that has a different composition. There are several different ways the particles making up the second phase can be incorporated into the material, and, unsurprisingly, they can significantly affect the properties of the material. Like grain boundaries, the boundaries between phases impede the motion of dislocations and increase a material's strength. Using heat treatment to intentionally produce a phase of uniformly dispersed particles with the goal of strengthening a material is called precipitation hardening. Pure iron goes through several phase transformations with changes in temperature. Below 912 degrees Celsius, it's in BCC form, which is called ferrite. Above 912 degrees, it changes from BCC to FCC, which is called austenite. It then changes back to BCC at 1394 degrees, and the melting point is at 1538 degrees, so above that, it's a liquid. The different solid phases are called allotropes of iron, and for convenience, a Greek letter is assigned to each one. We can extend this diagram to show how the phases within the material change with the presence of different amounts of carbon. This is what is called the phase diagram for the iron-carbon alloy. Because of the nature of the BCC structure, ferrite can only hold a very small amount of interstitial carbon. When the solubility of ferrite is exceeded, the extra carbon atoms have to go somewhere, and so a new phase called cementite forms alongside the ferrite. Cementite is a hard, brittle compound made up of 1 carbon atom for every 3 iron atoms, which corresponds to 6.7% carbon by weight. A 2-phase ferrite cementite material looks something like this. The exact way in which the 2 phases combine together within the material will depend on the amount of carbon and other factors, like how fast the material has been cooled. Because of its FCC structure, austenite can hold a much larger amount of interstitial carbon than the BCC structure of ferrite. But in the same way, if more carbon is added, we obtain a 2-phase material with austenite and cementite phases. There are several other possible phase combinations depending on the temperature and the amount of carbon present. The presence of a cement-type phase can have a significant strengthening effect, which is part of the reason steel is much stronger than pure iron. If you'd like to learn more, you can check out the extended version of this video over on Nebula, where I've covered phase diagrams in a bit more detail, including how 2 techniques, the tie-line method and the lever rule, can be used to figure out the composition and proportion of each of the different phases, and how it's possible to obtain phases like martensite that don't appear on the phase diagram. If you're a regular viewer, you'll know that Nebula is a streaming platform I've been building with a group of educational creators, including Real Engineering, Practical Engineering, Mustard, and many others. Nebula's packed full of thoughtful, entertaining, and educational content from independent creators, so it's only natural that we've teamed up with CuriosityStream, the best place on the internet to watch high-quality, big-budget documentaries, with quite literally thousands to choose from. So after you've watched my extended videos on Nebula, why not check out Ancient Engineering on CuriosityStream? A fascinating 10-episode show that explores how modern engineering is built on breakthroughs made centuries ago by ancient engineers, from genius solutions to irrigation and flooding problems, to the innovative designs used in ships, castles, and temples. Best of all, if you sign up to CuriosityStream using this link, you'll get 26% off the annual plan, and you'll get full access to Nebula for free for as long as you have CuriosityStream. It's the best deal in streaming, and signing up is a great way to support this channel. So head over to curiositystream.com/efficientengineer to get started. And that's it for this look at metals and alloying. Thanks for watching.